to begin, let's talk about where we are. And so we know a couple of really basic series that we're going to keep referring to over and over again. And they are the geometric series, which looks like AR to the n. And n is the index, so that's the thing that's changing. A is a fixed number, R is a fixed number. We know when that converges, it converges if and only if our number R is small, less than 1. In essence, it says, look, if R is small, it goes to 0 exponentially fast. And that's pretty fast. Now, the last time we said, here's another series, sum starting somewhere. And here, yeah, as long as it's positive, we're good to go. 1 over n to the power of p. Now again, n, that's what's changing. P is fixed. And we showed that that converges if and only if p is bigger than 1. This is called a p series. So we should probably write that down so we may remember these things. So this is our p series. And so it's a nice way to know when things converge. So these are sort of our two go-to standards. When we want to understand something, we say, okay, how can we relate it to one of these two things? Because these are things that we know pretty well. Now we do have some tests that we've talked about before. The nth term test, sometimes called the basic divergence test, and it says, suppose a sub n does not go to 0. So that's what that notation means here. So this means does not go to. So if it goes to something else or doesn't converge, it doesn't really matter. But as long as it's something other than 0, then the sum diverges. Why? Well, that's because the last term, if you think about the partial sums, they're not settling down. They're still bumping way up or oscillating. You need to settle to converge. The other test we have is the integral test, which says if you have a nice function which is continuous and decreasing, then the integral and the sum have similar behavior. In other words, they both converge or they both diverge. Now, they're not going to be equal in value, but it gives us a way to test whether something converges or diverges. So what we want to do is we want to add to our test. And so today we're going to talk about two tests. And one is called the comparison test, and the other one we'll get to later. It's also a comparison test. It's called the limit comparison test. So what does the comparison test say? Well, it says, let's compare a series to something that we already know about. And by the way, these are examples of series we already know about. And so how does it work? Suppose we have two sequences, an and bn. And an is strictly below bn, less than or equal to bn. And both of these are non-negative. Then what happens? Well, suppose that the an, if we add that up, that diverges. Well, what happens when we add up the bn? Well, if an diverges and an was positive, the only way it could diverge is if when we added everything up, it was infinitely big. So if there's infinite amount of stuff here, there has to be infinite amount of stuff there. So if the a sub n, the sum of that diverges, then the sum of the b sub n diverges. Now, on the other hand, if the bigger thing converges, then the smaller thing also converges. And that, again, the intuition makes sense because it says, hey, this bigger thing, there's not that much there. Converges means it's finite. And this is smaller than it. So it's also going to be finite. All right. So what's our goal? Well, our goal is we want to compare things. And whenever we're comparing, we always want to say, let's compare it to something simpler. And in essence, there's this word, find the essential behavior. You know, what's really causing the growth? What's making things get large or get small? And if we can understand that, we can say, okay, if we focus on that, we can use that to run comparisons. Now, a couple of things to keep in mind is it's really nice to know how do things compare in size. So here's an example of different things you might encounter out in the wild when you're dealing with sums. So we have factorials. They're at the top of the list of things that we commonly encounter. Are they the biggest thing? No. There's always something bigger. But they're pretty big. So factorials grow very quickly. So much so that factorials always grow bigger than an exponential, regardless of what choice of r you pick here. That's one of the things we actually saw earlier when we talked about sequences. And exponentials always grow bigger than any sort of polynomial. So n to the p, you can think of it as kind of like a polynomial term, n to a power. So exponentials beat polynomials. But polynomials, they beat logarithms. Because you could have like n to the 0.001. That grows really slow, but it still beats logarithms. Logarithms grow slower than n to any number. So logarithms are very slow. You might say, okay, do logarithms beat anything? Well, yes, logarithms definitely, they beat constants. And so it's important to sort of say, when you're trying to understand what's the behavior, you want to capture what's the thing that's big. Because when you think about it, look at the p-series. What are we trying to say? The p-series, we say something converged if and only if it was 1 over n to a big enough number. And in essence, what we're saying is 1 over n squared, that went to 0 fast enough that it converged. But 1 over, say, n to the half, it went to 0, but not fast enough. So in essence, a lot of our questions about do things converge or do things diverge come down to the question of, are you going to 0 fast enough? Well, whatever that might mean. All right, so let's do some examples. Okay. Now, something to keep in mind, there's a little tip here. If you want to have a smaller value, get a larger denominator. Now, why is that useful? Well, it's useful because remember, we're trying to make comparisons. So what we have is here, for example, let's focus on this left-hand example. We have a sum. This is a sequence inside here, and we're adding them up. So a series is a sum of a sequence. And that looks messy. And so what we want to do is we want to do a comparison. And one of the things you want to sort of get into the habit of is try to sort of guess what kind of comparison are we shooting for. So, for instance, do we think this would converge or diverge? If we were thinking it was going to converge, what we'd really like to do is find something bigger than it which converges, because then life is good. If we're thinking it diverges, then what we'd like to do is find something smaller than it which diverges. So it's kind of strange. It's before we answer the question, we kind of have to know what the answer is. So how do we get to that point where we know what the answer is before we even start? And the trick is to say, what matters? So let's think about it. We have n squared and sine squared of n. So if I have a really large value of n, they don't even have to be really large, like 10 or 100. Which one of these two terms is important? In other words, causes the number to be large or small? Well, 100 squared is pretty big. Sine squared of 100, though, can't be very big. See, sine squared, regardless of what you plug in, it's always between 0 and 1. So what that's signaling to us is it says, hey, this n squared, in essence, that's what's driving the behavior. And so you should think about what's happening. So let's suppose for a second we squinted and we didn't see that sine squared of n. And we said, okay, the sum of 1 over n squared. Does that converge? Well, the sum of 1 over n squared, it's a p-series. And p is 2. That's bigger than 1. So that does converge. So we're like, okay. So it's kind of like a p-series. So what we want to do is we want to compare it. So let's just ask the question, do we get a favorable comparison. So n squared plus sine squared of n and 1 over n squared. Now, which one is bigger? It's maybe not so obvious, right? So that's why there's that tip. Which one has a larger denominator? Well, they both have the n squared, but this has plus a little bit something bigger. So that's the larger denominator, so that's the smaller value. And now we can say certainly it's true that 0 is less or equal to 1 over n squared plus sine squared of n. Now, with our current way of thinking, we're thinking, okay, this is our a sub n, this is our b sub n, and now we can say, well, look, the sum of 1 over n squared from n equals 1 to infinity converges, and that's because it's a p-series. We know when they converge. So, since this sum converges, some of these terms converges, the sum of those terms also converge. So by comparison test, and it's important that we have this inequality here, the sum from 1 to infinity, 1 over n squared plus sine squared of n, also converges. And here, you'll see, we couldn't have done the integral test, because how would you integrate 1 over x squared plus sine squared of x? That's right, you wouldn't do it, because it can't be done. Okay, we couldn't do the divergence test, because the divergence test would tell us nothing. But what we said is, hey, comparison test, let's compare it to something that's favorable, easy to compare, and life is good. And life is better than good. It's beautiful. All right. Now, next one. Does the sum from 1 to infinity, 1 over n plus 2 to the n, converge? Again, we're coming to the place where we're not going to be finding values. We're only interested in, does it converge? Does it not converge? It's like we've become a binary, yes or no. So, now, what do we have? Well, we can say the following. Really, I have two terms here, n and 2 to the n. And it's true, because they're both positive, I could say, well, look, 1 over n plus 2 to the n, that's certainly less than or equal to 1 over n. And certainly greater than or equal to 0. Or I could say 0 is less than or equal to 1 over n plus 2 to the n, which is less than or equal to 1 over 2 to the n. Both these statements are true. They're absolutely both true. Are they both useful? Well, let's look at the first statement. So, this is what we're trying to figure out. What's true about this sum here? 1 over n. Well, if I add up the sum from 1 to infinity of 1 over n, what happens to that? What's that value? Now, this actually, we know what it is. It's infinity. And this has a name. It's the harmonic sum. It gets used a lot, so it's good to know that sum. So, given that we know that the sum of these terms converge, what can we conclude about that? And the answer is nothing, right? So, if we know that this sum is infinite, what we can conclude, our current conclusion is that the sum from 1 to infinity of 1 over n plus 2 to the n is less than or equal to infinity, which pretty much says it could be anything right now. So it's just not a very powerful conclusion to make. So here, this is an example of you want to be careful of what you compare it to. Now, that was if we used the 1 over n. What happens if we use the 1 over 2n? Well, that's the sum from 1 to infinity of 1 over 2 to the n. I can think of it as 1/2 to the n. Now, do we know what that sum is? Well, actually, we do. And it's 1/2 because the first term is n equals 1. 1/2 to the 1 is 1/2. Then at every stage we multiply by 1/2. So 1 over 1 minus 1/2, which turns out to be 1. Now, we don't actually care what the value is. The value is not important. But what's important is it converges to something. All right, so the sum from n equals 1 to infinity of 1 over 2 to the n converges. We just showed that. And now we can say, well, look, these terms, term by term, this is smaller. Why? Because larger denominator. And so, by comparison test, since the larger thing converges, then conclude that the smaller thing, namely 1 to infinity 1 over n plus 2 to the n, also converges. So we're looking at what happens to the larger thing, does that converge or not? And therefore we can make a conclusion about the smaller thing. Now, what could we have done at the beginning to know which route to take? Because we can see, if we focus on that piece, it doesn't help us. If we focus on that piece, life is good. Well, the answer is, what's the bigger thing? N or 2 to the n? Which term grows faster? What's controlling the growth? If we know what's controlling the growth, that tells us where to focus. The answer is that exponential grows a lot faster. So that's why we should say, look, when we're looking at what the behavior is, it's the 2 to the n that's going to help us make a decision. And that's going to be a theme that we're going to talk about in a few minutes going forward. But first, a few more examples. All right. So, next one. Does the sum 1 to infinity of 1 over root n minus 0.5 to the n converge? All right. So, now we have this sum. Okay. What can we do? Well, let's think about it. Now, again, we kind of want to get a good grasp on whether does this converge or does this diverge before we try to figure out how to show it. So it's like we want to know the answer before we begin. And with practice, you can do this. So what's the key? Well, thinking back to our previous problem, how do things grow? In other words, between the root n and the 0.5 to the n, which one gets bigger as we head off to n large? Now, you might think, oh, it's exponential, that should win, right? But look at that term there. It's exponential of a very small number. So when I take it to n, it's going to get smaller and smaller and smaller. So this is going to become sort of insignificant. So that says between the terms, really, it's behaving like root n. Okay, cool. Now we know what it behaves like. Therefore, we can say, since we know what it behaves like, we say, all right, ignore the 0.5 to the n, because that's the small thing for right now. The sum of 1 over square root of n. Does it converge or diverge? And how do you know? It diverges. Why? Well, because really, I can think of it as like the sum of 1 to infinity of 1 over n to the half, because square root of n is n to the 1/2. And this will diverge. And why will it diverge? Because it's a p series. It's a p series where p is a half. Okay, so, good. So, what does that tell us? Well, if we're going to do a comparison test, and right now we're in our comparison test mindset, well, that says I have the term here, 1 over square root of n minus 0.5 to the n, and I want that to be bigger than or equal to something, 0. And so the question is, what goes here in the middle? Well, what I need to put into the middle is I need to put something which will diverge, because my goal is to show that the sum here diverges. So I want to put something in here which diverges, but definitely goes in the middle. So, what can we do? Well, here we can take advantage of the fact that that's a minus. So it's root n minus something. Well, if I want a larger denominator, just get rid of the stuff that you subtract. 1 over root n. See, 1 over root n has a larger denominator than 1 over root n minus 0.5 to the n. Larger denominator, smaller number. So, now we have our conclusion. And what's our conclusion? Well, since this sum here is diverging, and we'll go ahead and rewrite this again, so we get used to writing this stuff down. Since we know that that diverges, it's a p-series, so that says this is already huge, this has got to be even bigger. So if that's even bigger, then the conclusion is that the sum of the bigger thing, it's also going to diverge. And so, I guess, an answer to the question, does it converge? No. All right, good. Now, what do we have here? Does the sum n equals 0 to infinity of 1 over n factorial converge? So, what does that sum look like? Well, 0 factorial, do you remember what 0 factorial is? So like 1 factorial, that's not so hard, that's 1. 2 factorial, that's 2 times 1, which is 2. 3 factorial, that's 3 times 2 times 1, which is 6. And so forth and so forth. So 4 factorial is 24. And they grow. They actually go pretty quickly. What's 0 factorial? Well, if you think about what factorial is, n factorial says start at n, multiply by n minus 1, multiply that by n minus 2, and keep going until you get down to 1. Now 0 factorial, what's the problem? Well, we can't even start, because we can't start anywhere and then multiply going down until we get to 1. So, what's the right answer? Well, here's the convention. The convention is that 0 factorial is 1. Now, one way to think about that is you could say, well, look, when you're doing factorials, normally you multiply n numbers together, like n factorial, you multiply n terms. 4 factorial multiplied by 4 terms, 3 factorial, 3 terms, 2 factorial, 2 terms. So 0 factorial says you multiply nothing together. Okay, well, if you multiply nothing together, what's the right value? And here's kind of the fun idea, is if you multiply nothing together, what you should get is what corresponds to sort of the multiplicative identity. In other words, what should you multiply by? What's the value where when you multiply by that number, nothing changes? And the answer is 1. It's sort of the analogous thing. Suppose I say, well, I don't add anything up. How much do I have? The answer is 0. Because, that's the additive identity. All right, anyways, sorry, we're getting distracted here. Now, what do we want to do? Well, do we think the sum of 1 over n factorial converges? Our belief is yes. Why? Well, n factorial is much bigger than exponential, because that's one of the things we just said. And exponential, they will converge, right? So if I had like 2 to the n instead of n factorial, it would be like, yeah, converge, no problem. Well, how do we argue it? Well, there's actually a lot of ways to argue it, but let's just make a silly, simple observation. Look, here's n factorial. All right. What is that? Well, that's n times n minus 1 times other stuff. So that's certainly bigger than or equal to n times n minus 1. All right. Well, that's good. Now, when is this true? Now, it's not true at the start, but certainly this step is as long as our n is at least 2. That's certainly a true statement. So it just says, take the first 2 terms. And now, here's another thing we could say. Well, look, if we subtract 1, well, that's certainly bigger than if we divide our n by 2, right? subtracting 1 is certainly going to make it only go down by a little bit, where divided by 2 makes it go down by a lot. Again, this is as long as n is at least 2. Now, you might say, well, wait a second, hold on. This says start at 0. We don't care about the first couple of terms, right? Where does convergence happen? Convergence doesn't happen at the start. The questions about convergence always ask you what's happening at the end. What's happening as you get close to infinity? So, what can we say? Well, we can say the sum from n equals 0 to infinity of 1 over n factorial, well, that's going to be the 1 over 0 factorial, which is 1, 1 over 1 factorial, which is 1, plus the sum n equals 2 to infinity of 1 over n factorial. And now the comparison test really is saying, let's just look at the sum. So I can replace the 1 over n factorial by this n squared over 2. So this is bigger than or equal to 1 plus the sum. Not bigger than or equal to, less than or equal to. Got to get my signs right, because we're flipping. N equals 2 to infinity, and when we flip, it'll be 2 over n squared. Now, does this converge? The answer is it converges. And why? Because it's a p-series. Now, the 2 doesn't matter, so it comes out. So this sum is definitely finite. It's going to be something small. So does it converge? The answer is yes. All right, good. Now, we're going to come back and visit this sum in a couple of weeks, but I'm going to go ahead and just mention something. Suppose we were to look at these values here. So what does this look like? Well, it looks like 1 over 1 plus 1 over 1. So it's like 1 over 1, 1 over 1, plus 1 over 2. So that's up to 2.5, plus 1 over 6, plus 1 over 24. The next term is 1 over 120, and so forth and so on. And does this equal a nice number? Well, it depends on your definition of nice, and I think it is. It turns out, and we'll show this, it'll be in a couple weeks, it turns out it's E. Or, you might remember that's the number 2.71828, ... So it's not so surprising that, see, look how close you are. After just the first 3 terms, you're already at 2.5, which means that from the 3rd term all the way off to infinity, you only have 0.21 left. Why? Well, because factorial goes to 0 really, really quickly. So anyways, yeah, this is going to be a really cool fact as we get later on. All right, now we talked about the comparison test. Let's talk about limit comparison test. Now, limit comparison test says, okay, suppose we have 2 sequences, an and bn, and we want to tie them together. And so what's true? What we're going to look at is we're going to look at the ratio of an over bn and say, all right, what happens to that as n goes to infinity? Well, there's a couple of cases. So there's a lot of information. Let's just focus on the first case. The first case says, suppose that they approach some fixed number L. Now, what does that tell us? Well, what it tells us here is that if you think about what this is saying, it says that A sub n is behaving like some constant B sub n. So that in particular, another way you could phrase this is that you could say, look, A sub n is less than or equal to L plus a little bit times B sub n, and greater than or equal to L minus a little bit times B sub n. That's what we mean when we say A sub n is approximately L times B sub n. It means that I can sandwich A sub n in between these two things. And now, if that's true, we can say, okay, Well, suppose that I knew that the sum of a sub n converged. Well, see, b sub n times some constant is below that, which means that the sum of the b sub n would converge. On the other hand, suppose I knew that the a sub n diverged. Then that says that the sum of this has to be huge, which means that the sum of this has to be huge, regardless of what that L plus epsilon is. So that must mean that the other sum diverges. So what you end up doing here is it says, hey, these two sums have to have the same behavior in terms of converging or diverging. And that is that they both converge or they both diverge. Okay, well that's if it approaches L. Now, what do we have? Suppose the limit as n goes to infinity of a sub n over b sub n is 0. Well, let's think about what that means. So n is going to infinity, so we're looking down at the end, and we're looking at a sub n versus b sub n. If this is going to 0, what does that say about the relative sizes of a sub n and b sub n? Which one has to be bigger for this to be true? Well, what has to be true is that a sub n is really a lot smaller than b sub n. So that's the only way that can happen. So if b sub n converge, then the a sub n also has to converge, right? Because this is a larger thing. If the larger thing converges, the smaller thing converges. Okay, well, what's the other case, the last case? Well, the last case is to say, well, suppose that a sub n over b sub n is huge, infinite. In the limit, of course, not for any particular n. Well, now, let's think about that. Which one has to be bigger? Well, what has to be bigger is the top. A sub n has to be bigger than the b sub n. So, if the b sub n is diverging, and a sub n is bigger than it, then the a sub n has to diverge. So these are all relatively about sizes. Now, I should say that each one of these three statements here, so a sub n is about L b sub n, a sub n is less than or equal to b sub n, or a sub n is greater than or equal to b sub n, it is meant to be when n is sufficiently large. Or in other words, in the tail. And that's where the convergence happens. Now, most of the time that we're going to use this this limit comparison test, we'll primarily focus on this first case. So that's our interesting case. When does the limit of a sub n over b sub n equal L? Now, what's our theme here? Well, what we're going to do now is say, let's capture the essence of the growth. And think of the rest of it as noise. So we're going to take out the noise, take out the muck and the noise. Get rid of it. Why? If we can take out the noise, then what remains is the pure behavior, the important part. So, let's think about it. 1 over n to the 0.99 plus a huge number. There's a bunch of zeros here. I think that's, well, let's see. We can probably figure this out. A billion. N to the 0.99 plus a billion. That's huge denominator. And so when you add up the terms, when you add up the first billion terms of this sum, you haven't even gotten to 1 yet. After adding up a billion terms, you're not even to 1. So that's got to be small, right? Because billion is a big number. So does it converge? You should be really suspicious the way I'm phrasing that. Okay, so yeah, let's be careful here. Just because the first 100, the first million, or the first billion terms are small, does not mean it's small enough. We got to think about it. And in particular, in this case, we have to say, okay, hold on. What's it really growing like? Because even small growth over time can still get huge in the long run. Infinity is a very long time. And these series, these sums, They're very patient. And so we got to make sure. Okay, so let's not be swayed by the fact that it grows slowly at the start. Now, what would we do? Well, what's driving the numerator, the top? Well, the top is just 1. All right. What's driving the denominator? Now, what do I mean by that? In the long run, as n gets big, which one of these two is going to matter more? The n to the 0.99 or the billion? It's going to take a long time, but eventually n to the 0.99 will start to get bigger than a billion. So downstairs, it's n to the 0.99. So what we can do here is we'll do the following. We're going to think of this as our a sub n, our whole expression, and we're going to let b sub n be just the parts which have the growth of the upstairs and the downstairs. Now, first step, let's look at the limit as n goes to infinity of a sub n divided by b sub n. Okay, so that's the limit as n goes to infinity of, well, a sub n, that's 1 over n to the 0.99 plus a billion, and divided that by b sub n. Since I'm dividing by b sub n, I can think about flipping b sub n. So that's n to the 0.99 over 1. All right. Now, what can we do? Well, let's slow it down. Why? Well, notice that the top, n to the 0.99, is going to get big as we go to infinity. And we're not going to slow it down by doing some L'Hopital. We'll slow it down using algebra. So let's multiply both the top and the bottom by that growth, reciprocated. In other words, we're going to cancel out that growth. So multiply top and bottom by n to the minus 0.99. And if we do that, we're going to get, this is the limit as n goes to infinity, and upstairs we're going to get 1 times n to the 0.99 times n to the minus 0.99, which is 1. And downstairs we're going to get 1 plus a billion, which is a lot of zeros, times n to the minus 0.99. Okay, what happens? N goes off to infinity, and as it does that, what happens to our terms? Well, the top goes to 1. The denominator goes to 1 plus a billion times 0. That negative in the exponent is going to drive it down to a small number. It's going to go down to 0, which is 1. Now, what's our conclusion? Our conclusion is, because this ratio goes to 1, that says, lo and behold, if I want to know this sum, I want to compare it to the other sum n equals 3 to infinity of 1 over n to the 0.99. These two sums are going to have the same behavior. In other words, they're going to both converge, or they're going to both diverge. So, the last question for us to ask is, well, which behavior does this sum have? And you'll notice this is an easier sum to work with because we've gotten rid of that distracting a billion. We're not tempted by a billion anymore. Well, what kind of sum is this? It's a p-series. Is it a p-series that converges or diverges? Well, 0.99 is not bigger than 1. So, since this sum is a diverging sum, and the reason it diverges, it's a p-series. See, that's why it's nice to have p-series, because a lot of things get compared to p-series. Original sum also diverges. And by what test? Well, by the limit comparison test. And there we go. All right, good, good. Now you might wonder, hey, could we have used a normal comparison test? And in essence, yes, but in practice, why? Why do I make the sound? Well, here's the challenge. What would we compare it to? See, if we want to compare it to something, we would say, well, look, we think it's going to diverge. Why? Well, because we actually know it's going to diverge, right? Because we already showed that. So in order for us to make that work, we need to get this bigger than or equal to something that also diverges. Now, the question is, well, what could you put here? Now, you'd like to say, hey, let's just get rid of the billion. But the problem is, if you get rid of the billion, what's left, 1 over n to the 0.99, it's actually going to be over here. So it's the wrong direction. See, if n to the 0.99 was here, it'd be like, woohoo, we're done. But because it's on that side, we get no conclusion. Now, it is possible to gently massage this to work, but it's not easy. It's actually kind of tricky. But because you have a limit comparison test, what really saves you is you say, look, the part that makes it tricky is at the start, it really is very, very, very small, super, super small. And it's only in the long run that you really start to get this n to the 0.99 dominating. But the limit comparison test says, I'm only going to really look at things in the long run and look at the part that dominates. And that's why it definitely is, limit comparison is our better tool. All right, well, let's do our next example. Okay, use all of our tests so far because, well, you know, there's always going to be another test, right? There's so much to learn. And we're going to decide whether this sum, 1 to infinity of 1 over n cubed plus n, converges. Okay, so let's talk about our test. So we have the nth term test. Okay, what does that tell us? Well, we're going to look at the following. We would say, look at the limit as n goes to infinity of just the term. So this is our a sub n here. Of a sub n, well, that's the limit as n goes to infinity of 1 over n cubed plus n. And what does that go to? It goes to 0. Okay, so by the nth term test, the terms go to 0. What's our conclusion? Well, the conclusion is no conclusion, right? Because in the nth term test, if your terms go to 0, you don't know. Okay, so we don't know yet, just by the nth term test, if this converges or diverges. All right, so that was one of our tests. And in some sense, the nth term test, easy test to apply, but because it's so easy, it's kind of weak. And there's a lot of things it can't distinguish. Now, let's talk about the integral test. Now, the integral test says, let's think about this as a function. And so what's our function? So our function here, well, if we think of our f of n is 1 over n cubed plus n, then we should really think about this as saying, let's look at f of x as 1 over x cubed plus x. So we're going to look at the integral 1 to infinity. And this is, by the way, it's a nice function. It's a continuous function. And it goes to 0. And so, all right. So we can apply our test. 1 divided by x cubed plus x. All right. Well, that means we actually have to integrate it, right? Because we got to do the test. Now, 1 over x cubed plus x, that's the same as x times x squared plus 1. We can factor. And how do we integrate something like 1 over x times x squared plus 1? Is there Any technique which we might be partial to using here? Anything come to mind? Is that how we could deal with this fraction? Yeah, this is partial fractions, right? Okay, so algebra on the side. Woohoo! Algebra on the side. Algebra on the side. Hi-ho, dairy-o, it's algebra on the side. All right. Whoops, I got too excited because of the song. 1 over x times x squared plus 1, that's a over x plus b over x squared plus 1. Clear your denominators. 1 equals a times x squared plus 1 plus b times x. Right? Oh my gosh. It's been too long. Where's my mistake? Do you see it? Can you see it? I set it up wrong. See, this x squared plus 1, that doesn't factor, so it needs to be bx plus c. So it's bx plus c times x. There we go. Now we're cooking. I should have known something was wrong, because look, this is a cubic, so you should have 3 unknowns up there. Now, well, there's not a lot of things that we see right away, but let's do our expanding group. So, let's look at our x squared terms. Well, we have an a, and we're going to get a b, right, because it's bx squared. And then, let's look at our x terms. Well, not many of them. There's actually just one of them, c times x. And how about our constant terms? Well, not many of those either, plus a. Now, what has to be true? Well, if we think of this as a polynomial on the left and a polynomial on the right, the coefficients have to match, which means a has to be 1, c has to be 0, because there's no x term, and a plus b has to be 0. And so what's our conclusion? Our conclusion is a equals 1, b equals minus 1, c equals 0. Okay, so back to our problem. So this becomes equal to the integral 1 to infinity of, and then we have a 1 over x minus x over x squared plus 1. Now, these are things we can integrate, right? So that's log of x minus and x over x squared plus 1. It's not arctangent, because if you think about it, what can you do? Well, if you think about the denominator as being our u, x squared plus 1, the derivative of that would be 2x, which is almost our numerator. We're only off by a factor of 2. So it turns out this is 1/2 log of x squared plus 1. All right, so evaluate that from 1 to infinity. Okay, well, what can we do here? That is, if we clean it up, you see right now when we try to plug in infinity, we're going to get something which is huge, subtract something which is huge. So we're going to get something which is indeterminate. So we're not going to quite plug in infinity. Of course, we never plug in infinity. But we want to clean it up so it's something that we can actually figure out. I can combine these two logs into a single log. So I can write this as log of x, and then this minus means we divide. This 1/2 needs to come in, and it's going to come in as an exponent. So the half here is going to come in upstairs. So that's going to be x squared plus 1 to the half, or if you like, the square root of x squared plus 1. Now, that's what I need to evaluate. But of course, we can do even better. And how do we do even better? Well, again, on this side we get a big thing over a big thing. And what we can do is I can come on the inside, doing some really careful algebra here, and I'm going to multiply by 1 over x and 1 over x inside the log. Perfectly fine, right? Because I'm multiplying by 1. So that would be log of 1. And then the 1 over x, I can bring it into the square root as a square root of x squared. And that becomes square root of 1 plus 1 over x squared. All right, good. Now I can plug things in. So as we plug in infinity, so in other words, what happens to our expression as x gets bigger and bigger? Well, the only place x shows up is right there. That's going to make that term go to 0, which means we're going to get log of 1, which is 0. Then subtract. What's when we plug in 1? Well, we're going to get log of 1 over 1 plus 1. So log of, 1 over square root of 2. Now, do I care about the value? No, not important. What do I care about? The fact that it's a finite value. Okay, so since the integral converges, what's the conclusion? See, remember, what does the integral test say? The integral test says, hey, do the integral of the series and then look at that, and then if the integral converges, then the sum converges. And if the integral diverges, then the sum diverges. So since the integral converges, then the sum also converges. All right, so now we know the answer, that it's going to converge. And there's the work if we did the integral test. You'll notice that was quite a bit of work there. All right, now what's our next test? Well, comparison test. Now, before we do a comparison test, we really like to try to get an idea, do we think this will converge or diverge? Well, I think it's going to converge. The reason I think it's going to converge is because we just showed it converges. Okay, suppose we hadn't done the work. Well, what we could do is we could say, let's look at our sum and say, okay, well, the n cubed plus n, which part is really the big part, the thing that's going to make it get large? Well, it's the n cubed. So to me, it looks like a 1 over n cubed. So we say, okay, if it looks like a 1 over n cubed, that's something which converges. So what we want to do is we say, all right, if we think it's converging, we want to make something that's a little bit bigger than that will also converge. And of course, we want to make sure this is not negative, and it's true. Our 1 over n cubed plus n is certainly never going to be negative. So, can we fit something in here which converges? Well, the answer is we just take out the plus n. And if we take out the plus n, our denominator is going to be 1 over n cubed. It's a smaller denominator, therefore it's a larger value. All right. And so we set that up. And we can probably add in the phrase we have, that this is true. And we know that the sum from n equals 1 to infinity of 1 over n cubed converges. Why do we know that? What's true about that? Well, P series. So the conclusion is that by comparison test, then the sum from 1 to infinity of 1 over n cubed plus n converges. So why? Well, because we fit 1 over n cubed plus n below something which converges, and therefore it must also converge. Okay, there's one more test that we've done, and remember it said all of our tests. All of our tests. So what's the other test? It is limit comparison test. Now, limit comparison test is a little bit more general than the comparison test. And but in some sense, we're going to feel like it has the same sort of behavior. So the way I like to think about limit comparison tests is say, what's important? What's important? So we're going to think of our a sub n, that's 1 over n cubed plus n. Now our b sub n, we want that to be something which has the same growth, but a simpler expression. So in essence, we're sort of stripping away all the unhelpful parts. Well, what's an unhelpful part? With a plus n, very unhelpful. So, because the n cubed, that's our growth. So 1 over n cubed. All right, so here's our two sequences. Now, take a look at the limit as n goes to infinity of a sub n divided by b sub n. Well, if we write down what that is, that's the limit as n goes to infinity, and it's 1 over n cubed plus n times b sub n, flip it over, n cubed over 1. And if we clean that up, which we might as well, what happens? Well, n cubed over n cubed plus n. Now you could do L'Hopital here, and it would work, but let's just sort of do the philosophy. Slow it down. We're going to slow it down. All right, so how do you slow it down? Well, let's multiply the top by the growth. Divide out, n cubed. Multiply the bottom by the growth, n cubed. And you'll see it's the case that we've rigged it. In fact, the way that we want to use the limit comparison test is we want to choose things so that the growths are the same. We always try to shoot to say, let's pick our b sub n so it grows like a sub n, just a little bit simpler expression. And all right, so what happens? Well, if you do that, you see that this becomes a limit as n goes to infinity of 1 over 1 plus 1 over n squared. And now, easy to take that limit. It's going to go to 1 over 1 plus 0, which is just 1. Okay, well, what's our conclusion? Well, that's a 1. Well, what that means is that whatever the sum of n, 1 over n cubed plus n does, the sum of 1 over n cubed does. But the sum of 1 over n cubed is much easier. So, by the limit comparison test, since the sum of 1 over n cubed converges, and again, you should always explain why things are true, it's a p-series, then our original sum, 1 over n cubed plus n, also converges. Because the limit comparison test says these two sums have to have the same behavior. It's a lot like the integral test. The integral test says, hey, the integral and the sum have the same behavior. Limit comparison test, these two sums have the same behavior. But, all right. Now, the question arises, which ones should you know? The answer is you really should know all of them. But in practice, what you should focus on is the limit comparison test is very helpful to simplify your expressions. We say, let's apply the limit comparison test and get rid of all this excess noise and say, what's it really behaving like? Once you've applied the limit comparison test, you may not be completely done, but you've simplified it oftentimes enough that you can now apply an integral test or a comparison test in a much simpler fashion. So just be open to possibilities. And well, I think our time is maybe up now. So, well, we'll save the last example for a future lecture, right? We have more of these coming. And that's it for now. And see you next time. Bye.